Okay, so let's get started. Welcome everyone to another week seminar. And today we have Sofia, as you probably already know. Sofia is a member of LEAP working in the neutrino and DOJ groups, and also on the geography project, which was actually our last seminar. So just to give you a bit of background, Sofia did her PhD back in 2003, working on the Delta experience at LEAP. After a postdoc in the decay experiment, working with neutrino oscillations, finally joined OJ and the neutrino group for us about the same time, by then SNO group, co-founded the SNO plus collaboration, and Sofia became the convener of the SNO plus anti-neutrino group. So today, actually, she will focus about the latest collaboration results. Actually, the first anti-neutrino with the SNO plus water phase, which not only was accepted for a few rounds, but also selected as many suggestions for highlights. So, Sofia, please go ahead.
Okay. Good morning. So this is I'll present mostly the results of the measurement of the neutrinos in water. I will. This word. It doesn't work. Okay. Done. Okay. So I will try to follow this outline. So I'll do an introduction with the historical. Put some into context what we are doing. So start by discovery of neutrino oscillations and then towards the large detectors and SNO plus. And then I will spend, I think, maybe most of the time on the calibration for the antineutrino measurements that we did in the water phase, and then go to the result of the reactor antineutrino in pure water, and then I try to put it back into context. Okay. So I start by the neutrino discovery. As you know, the neutrino was proposed by Pauli as a desperate remedy to explain the lack of energy conservation in deep decays. When an neutron just runs a proton, and then you have an electron, and then this is measured, and then this is a continuous spectrum. So there should be another particle that most probably we cannot see. We cannot clearly not seen in the experiment of beta decay. It is we know it has to be light because the spectrum spans almost to the end of the available energy, and it might not interact. But we know that it interacts quickly, and we can invert this diagram and use inverse beta decay, in which this particle, which is an antineutrino just for particle number conservation, antineutrino can interact with a proton in any material and then produce a positron and a neutron. And so 25 years later, this experiment was done by Ramsey, and actually the first idea was that, well, we do need to have a very strong source of neutrinos, and maybe you could use like a nuclear explosion. And well, fortunately this didn't go on, and they didn't start a reactor. So nuclear reactors produce large numbers of neutrinos, and then what happens? So the neutrino will get to the detector, we get to the protons, it will interact there, creating positron and a neutron. Well, listen, I went to check the writing for an experiment because someone asked me, like, they also saw neutrinos in water. Yes, so they use a water tank, and it's true. But they actually use a more clever setup technologies. So just to start with the things, so the positron is easily seen, as you can imagine, because it will annihilate very rapidly with an electron in the reflector material, and it will produce back-to-back gamma rays. The neutrons are more difficult to detect, of course, because they are neutral. They will scatter around the material. They lose energy very fast, especially if you have big protons, because neutrons and protons have the same mass. Then they will leave half of their energy to the proton at each time, and then they are captured. And when they are captured, this means that when they are very low energy, they just can get to one of the neutrons in the material and create a bound state. This can happen also with free protons, the hydrogen in water, and it will release then it's a deuterium in a cycle state. It releases the gamma rays. And in their case, they use cadmium inside the water because this produces more light. So it has two things. One, it captures the neutron much faster because I have a section from neutron capture. And then it creates a high energy signal that in addition is multiple gamma rays. And this is very useful for their setup. Because as you can imagine, they have here the water targets, but they are 11 meters from the reactor, 12 meters underground. So they have lots of atmospheric ions going through and lots of noise from the reactor. So what they do is that they have a very thin water target where all this happens, and then we will see for the positron annihilation, two back-to-back gammas. And you can do this for this target. You will see one gamma in the detector 1, and then the detector 2, and nothing here. And then just few microseconds later, you will see again signals in these two detectors, but nothing in the other. So with these, so for the texture, they actually use with the scintillator, and then each of them is overseen by an independent. But the good thing is that they can use these two targets to find this coincidence of coincidences, let's say, and measure the ones that are not correlated with the two detectors, and so oscillators. Okay, and they had a signal detector of 4, 1 event per hour, and they also just check by turning the reactor off. Okay, much later, and 25 years later or something, people are now using neutrinos to much larger neutrino detectors to study natural neutrino sources. Then the spots are lower, you have a source, and huge detectors. This is a photo of the superconductor method, and this is a photo of the SNO detector. And these are always in the ground for showing the cosmic rays in case of chemicals from 1,500 meters underground. SNO plus a SNO is 2,000 meters underground, and they are very, very large. So the Super K has 50 kiloton of water, and the SNO at 1 kiloton of heavy water, and then they are followed by many, many UTs, in this case, 12,000 in these days. 9,000. And okay, this is just there. I wanted to put my photo in the Super K, but then they're just in snow plus. Okay, so this is where the dimensional oscillations were discovered, right? So using the atmospheric neutrinos created by the cosmic ray that creates neutrinos and electroneutrinos. So can show that while the electroneutrinos follow the expectations, the neutrinos. In the case of SNO, they search for neutrinos from the sun, and that's a very clever way of counting utilities for the sun. So in fusion reactions. And they had a clever way of finding, of measuring the electroneutrinos, but also the total number of neutrinos by using neutral current interactions made possible by the everywhere. And then, this is to continue the story. After this was done, then we had to then these were confirmed with human-made neutrinos. So in the case of superconductor, in the case of atmospheric neutrino oscillations, or even neutrino interference, this was confirmed by K2K, which is K2K, or K2K. using the use of neutrinos and then also antineutrinos and confirm that the result of the bottom shot from very far away, from 4 to 280 meters. In the case of solar neutrino oscillations, this first confirmed with Cameron by looking at reactor incidents, again from very far away, so 150 kilometers. And they've shown that the results are compatible. So the same oscillation that appears in the sun inside the solar network also happens in vacuum and with the anti-particle. And then to measure, there's of course 3 neutrinos, so 3 mixing angles. The third mixing angle was then discovered by AmBe. You see again reactions neutrinos very close, much closer to the reactors that one. This is the last mixing angle that was from here, we continue back to solar, to natural sources. We have borate SNOs studying solar electron neutrinos, and also antineutrinos created now by fission reactions. And then, okay, this here I marked in blue the experiments that are in water, and here the ones that are in scintillators. So we see all the antineutrinos are in channels, so the low energy ones. And then going to water, I also ice cube, just to remind you how easy it is to use water. Okay, so from snow to snow plus. So this measurement of snow was to measure the solar neutrinos, as I told you, in different channels, and mainly in the elastic scattering, in which all kinds of all the 3 types of neutrinos are mixed, and that was measured with my precision by just a figure. And then charged currents that are almost sensitive to electron neutrinos, and the neutral currents, which they confirm the solar model. This is a very, very nice picture, as I've shown you, very big and useful, and so we then decided to transform it into studying now, not for this is to prove that neutrons have mass, right? But now we want to know which is the mass mechanism. And so the discovery of neutrino mass disrupted the standard model, but in the case of neutrinos, because they have no charge, we don't know exactly what is the mass mechanism in which it is. They can be major particles, in which the particle and the antiparticle are the same. And so the way to search for this is to look for double beta decays. So there's a few isotopes that have 2 beta decays at the same time. If the neutrino is so antiparticle, then you can close this loop, and then you'll have a little bump in the total release, then the total energy of the electrons. So this is the main goal of SNO+, but we are adapting the SNO detector that is going to conquer the water. And so for this we created a series of phases in which you can do different physics. So I will talk mostly about the results of water phase. I will show you in my last slide something from the partial field phase, in which the detector was half water, half scintillator. And we are now on the scintillator phase. Later on, we will have beryllium, so on. And then, of course, you can even adapt. If we do find double beta decay, then you can do either more beryllium or other isotopes. Okay, so this is what we can do for oscillations during the phase in which the detector is a scintillator. So here are what we could measure from solar neutrinos, and these are the reactor neutrinos in small plasma, and it would be very interesting in principle to measure both at the same time, because as I told you, we have the solar neutrino measurements are very sensitive to the mixing angle, but not as sensitive to the mass difference between the 2 neutrinos involved. This very precise measurement of mass difference comes from Kalman, because the only experiment that made it. These are the results now from the solar neutrinos, from latest results from Americana. And what you see is when we do the global fit of the mixing angle plus the mass differences, the best fit is not totally compatible. We could, because it's because we can redo these measurements, and this would be the two different spectra that we use. Okay. Now, in contrast, that solar neutrinos we can measure also, but there are many backgrounds, and of course, in scintillator there is no direction, contrary to the evolution of detectors, so this is a bit more difficult level. And there's also no coincidence starting as in the case of the neutrinos, in which you see that we don't even put background in these plots. So these are all reactors, and this is the geoneutrinos that come from the Okay, this is because these spectrums arise from mainly three nuclear power stations in Canada. So there's one of them is at 140 meters and dominates our plots. Then I got 200 meters. So the oscillations, of course, go the missing angle, and then the delta square distance and the energy. And so these two distances create this very strong oscillation. The Canadian reactors use heavy water, so they are power. What it means for power heavy water reactor, pressure heavy water reactors. That's where SNO got heavy. And in this case, we have access to the electrical power data from Canada authorities, and we can model how many neutrinos we are expecting at each moment. We had also 100 more cores in the US, which have an average baseline of 650 liters, and for which we only have monthly average flux from the international calibration. Okay, these are the different concentrations of the several main isotopes in the reactors. So this is, of course, the signal that we are going out that we see with water. Here we have indication that there is some systematic uncertainty from this that is largely dominated by our uncertainties. Okay, so the Snowbus detector in more details, it's 1,007 meter underground at small lab. So this is an active mine in which the SNO experiment was installed, and then this was expanded to a much bigger lab. The big thing of being so big is that we have only 3 meters per hour, and so we can easily veto the following 20 seconds or even 1 minute to avoid plasmogenic induced backgrounds in the active medium. The active medium is in SNO and SNO plus is here enclosed in an acrylic vessel, and is a 12-meter diameter sphere. The acrylic vessel is very transparent, in fact, 5 centimeter thick enclosure. And then all of this carbon is filled with pure water. And here at around 8.5 meters, we have the 9,000 plus. So in SNO, this was full of heavy water, and it was of course heavier than the water around, and they had to have some rocks to hold the detector in place. When we changed the scintillator, scintillator is lighter than the heavy water, and then we have this other rock system. So you see that this holding down rock system will take some of the light away from this region. Okay, also the scintillator will have much higher rates, so there was also like detectors. And of course, in addition to water purification plant that was already available, we also need to create scintillator in the ground. Also for the purity, we had to design the cover gas system and also the calibration deployment systems. And we have a new array, new simulation tool, and an array of photo cameras. This just show you detectors will be working. Okay, so I don't know. Yeah, I'm already super late. Yeah, so these are the first physics results from the water test. We had, because of physics, started just showed on the detectors and so on, searching for invisible modes of neutrino decay. This means neutrons, protons, or two protons, or neutrino proton decaying into invisible states. So no, so there's only the excitation of gamma from the produced isotope. So this is oxygen turning into something else, and very limits on the very long lifetime. And then the other one was to do the measurement of solar neutrino flux with very low background. And here I show you the measurement when we ask that the energy carried by the produced electron is about 6 MeV. If we go down to 5, then we start having backgrounds in this region that doesn't work. For reference, in the other SNO lowest energy analysis, the new super K analysis go down to 3.5 MeV, but again, we also have this. So yeah, that knows. Okay. To make these measurements, we have to, of course, calibrate the local detector, and this calibration is not only used for the water, because we will in any case have water outside the detector, and we also have to characterize it in this process. So here I show you the results. Actually, the work of Sofia Andringa. That compares the angular response of the PMTs in the several phases, and then in SNO class, and which it could be extended to much higher angles, which means that we can get signals closer to the PMTs, which is good for us now because we have water both inside and outside the vessel. So for the first time, we're trying to use also the outside part. Okay, and these are then. So this is done using a laser bulb that emits the light, but then you want to know also what is the response to particles, and for this we have N-speed spin source, in which there will be a beta decay that can be tapped inside the source, and then we will have a 6.1 MeV gamma from oxygen, unsecond oxygen. And with this, it's just show you that our Monte Carlo will reproduce well the energy distribution, the source, the position, the construction, and the construction. Okay. More interesting, we also have another source which gives us much lower energy gammas, actually at 4.4 and a 2.2 MeV. So we see really lowering the energies we can test, and this is also our anti-neutrino conversions. Okay, so this is our just schematics of what we can do for calibration effects. Actually, this calibration moving things for the sources was done idea. We also did other that I will not tell you what just when I will. Okay, anyway, so we can put the source inside from here from the net, and then move it around here on the side, which going to then the outside. In this case of the source, so I'm using beryllium. So the beryllium will have an alpha decay, and this alpha will be will interact with the beryllium, create the carbon and the neutron. This carbon, 60% of the time is in excited state and will release this 4.4 energy down. Okay. The neutron will then be thermalized in the detector, captured by a proton, creating this neutron that will give this 2.2 energy down. Yeah, this has there are some cases in which the carbon is in ground state, so we have no tap, but we also always have the limit. And this is nice because this is exactly the signature that we look for in the so we'll have a prompt thing at 1.4 energy gamma, here in the fixed energy, which is good. In the case of the antineutrinos of inverse decay, this would be our positron. Okay, so this mimics our positron. And then we have the same kind of, well, same neutron, actually slightly higher energies in the source, but this increases energy very fast, doesn't make much of a difference. And then it will capture, and then there is the gamma that we use for okay. So we did calibration campaigns in 2018, putting the source in all these positions. And this is as a function of the minimum number of EMTs that get a signal, the rates that we measure. So we see that we were measuring the time rates here, figuring at around kilohertz, a bit reduced here because after cuts against instrumental backgrounds. And here you see clearly the signal of this 4.4 energy gamma. The 2.2 energy gamma is somewhere here in the okay, and these are the results that we got. Actually, we can capture, or we can measure, we can trigger, let's say. Well, so if I try to analyze how many particles are there, then I can know how many times the detector was triggered by the DC capture, and this is around 50% in the center of the detector. And then it drops. It drops, of course, because here on the top we have less coverage for the lights, so it drops there faster than the bottom. And then here it also drops quite fast, but shows that we have a non-negligible efficiency to also use a much larger volume. So this is the highest efficiency for detecting visual energies that was achieved in the Cherenkov detectors. Okay, so how do we do this? So just by looking at it, it's very complicated. But fortunately, from the beginning, and it was actually only a very nice suggestion from Baran, we thought, okay, we can just change this threshold. So the minimum number of bits of PNPs that we look at to select the signals. So here, I can change here the threshold, and then look at the time between subsequent events. And this creates curves like that, in which you see we have a very large number of very fast incidences. This will be our signal, and then in principle we would like to have then a flat background, but this is not true because already so high that even there is a non-flat background. So in this so here we are. So we have to describe these curves. We are looking at the rate that is given by where we set the prompt event rate. The prompt event rate. So we are asking for first signal with a high number of copies. And then we look at the delayed rate, so that is a very low energy signal that is very, very high rate. And okay, so with this formula we will take all these Okay, so we will measure the purity for our selection, the efficiency for our triggering of the neutrons, even if we cannot really point them out, and the capture time and capture rate that is the characteristic of neutron capture in water. And it's okay. So here I show you for examples so that you can get purity of high purity if we put the very high threshold for the prompt event, but we get the efficiency of around 40–80%. For the study that showed the numbers from the questions. Okay, and now by analyzing these results as a function of the cuts that we are doing, we can then also spectral limit. And there are that is very well. So these are the main results efficiency that I told you. So we have almost 50% trigger efficiency at the center of the detector, and this will be flat up in the region that we usually use for analysis for the neutrinos that I've shown, and we've shown that it also is for the external water. So it's certainly the main results that are important for the anti-neutrino stage. Notice here that there is systematics, first because the source, so the source is americium and beryllium in the powder, so it has to be inside container and so on, and this creates some losses there. And then the other one is from the rate fluctuation. So at the background rate fluctuates, then we will measure systematic neural efficiency. This is correctly defined result. The other result of this part 2 is that we measure the lifetime of the neutron that is captured in water, and we measure this number, and then we also have corrections from the source encapsulation, the same one, and from the rate, and we get this final number, which is very compatible as the ones measured by Super K. But we did a clever thing, which was to combine all the data, reduce very much the statistical uncertainty, and even the flatness is not so big, so we have a much more precise result. So this we published as a measurement of neutron proton capture in the Snowflake water phase. So we just invert this tau to get the sigma, and we get this number, which is quite compatible with old measurements, so nothing new there. The old measurements are even quite more precise, but they are often very, very different. So this was the older measurements were all obtained by shooting a very intense pulse of neutrons into water, and then waiting to see how long this stay in water. And in fact, they were also dominated by statistical uncertainty. They looked at some systematics, but very few. So the neutron spectra and the temperature, we also evaluated, whereas they are also negligible. This uncertainty of theirs is statistical. We are dominated by systematics with cross-checking. Okay, so this we published in 2020, and then we spent a lot of time to get for the evidence of neutrinos that I promised I would show you. So even before that, so you see here that we always have very high tech, very good for researches. So it's still in the segment where we have a cross-check measurement in which you do a much higher purity selection. This is based actually on the way trigger that was developed by Sofia Andringa, also to see antineutrinos, but not reactors, because they won't trigger at higher temperatures. So what do they do? And what did we do here? More precise. So here we had no reconstruction at all, just trigger level information. In this case, we reconstruct just the prompt event, so the highest energy event. And then we ask that the second one is not only closed in time, as shown here, so we can see them fast, we just analyze. We ask that at least 4 of the PMT signals there are compatible with the position of the first event. So we get the first event, and then of course we have to correct for the time that light gets from this point of interaction to the neutrinos. So we need to correct for that, and using that and then selecting that these hits are very, in our case, 12 nanoseconds, are compatible with this position within 12 nanoseconds. Then we can increase the purity by a factor of 3.5 by reducing just little the efficiency. So this, I think it's important to note that this can be used to purify the sample even without reconstructing the second part, the neutron capture event. So this is superconductor is at around life now, but it's in its last version. What they did was to change the trigger strategy. So what they do now, they record always at 16 kilohertz. They record the small node of their frequencies, and then they the software trigger that searches for coincidences within 200 nanoseconds, and that's what they call events. And if there's a super high energy event, which always have then they use all the subsequent hits out to 500 microseconds and make this test, right? Are these hits compatible with coming from a second particle in the same position? And so here is from their paper. What's this? So it's not so different from us. They have 30% efficiency from start, as they ask this 7 hits to be compatible with. They are not even, but 7 hits compatible with the front position, and then they do more geometrical cuts on these different hits, always without reconstructing the event, and then finally they do a calibration. They get to around 18%, and if I understand correctly, now with machine learning, for this timing. But the crucial thing is that they can only do this for high energy events, not for there's no time process. Okay, so the snowplus antineutrinos. We use two statistical methods that here I'm showing for one how the data reduction is done. So we keep low energy events also offline, only if they are within 1,000 microseconds from a well reconstructed event that has to have more than 15 minutes, which is the region where we are very confident that everything works very well. So this is 160.4 expected reactor antineutrinos that were simulated up to the PMT region. And then we see how many are triggered in the simulation, and it's 33%. Then we do this instrumental, this is next. Then when we cut on the number of hits of the consequence and also the related event, this reduces a bit the efficiency. This also to note that many of our positons will also be below threshold in measurements. And then we make this time cut of 1,000 microseconds. This is almost all event, and this is the data that we can do. So we start with 14% of the original ones, but we have millions of accidental background. And then so we purify the first event, then we put visual volume cuts. This is to avoid, because we have more background next to the recruited vessel, so we will have the internal region of the external region, but not this region very, very close to the fluid. Then we do another cut on energy, which is quite similar to the orbits, but it's just a cluster cutter reconstruction. And then on the distance between the events, and we get, well, very small number of antineutrinos expected, but also but a very large number of backgrounds. And then we use these two different statistical methods that can also deduction. So with two-line analysis, this is important because it's a very, very rare signal. If we expect 5.3, 7.7. We better not look at that, if not, we will always keep one more. So the selection is then finally asking for coincidences in time between 3 and 500 microseconds. But what we do is we test everything in the cycle. As I told you, we cut near the region closer to the Grumman castle, and then we cut also. We also have a higher limit for the energy of ground event because the reactor sector stands around 280 MeV, and above that we will have further hindrance. This was also cross-checked sometimes that our expectations. And then we need the final step, which reduces for 10 factor 10,000, and we use these two analyses. So the first one is a likelihood ratio, so more classical IBD like events versus random background. The random background PDFs are created just easily by looking at the singles events that we pass the first selection for one signal for the delay signal, and this is the energy and shape parameters of this measured data to be our function. The radial position and also if the particles coming from inside or outside, and then the delta P and the delta. So the distance in time and the position. And the other one is these two boosted decision trees. So first one select a very big front, a positron, and then the second one selects a neutron. This is again more similar to what forthcoming can be done. So it's a problem that the construction was that proposed this analysis, and so they use the same variables, shape variables from SNO and from SNO plus. So this ITR is the in-time ratio, so the number of hits that are closer in time in relation to of the event of the reconstructed event. But they use also this analysis uses also these other variables that do not rely on the reconstructed. And you see that in the end they are quite similar. They were optimized for different slightly different working points, but they are So this one allows a bit more of accidentals, a bit more of everything actually, but with similar performances. Okay, and so this is I come to the 3.5 in evidence. So first I want to show you this is how the final selection works. So there is here the black dots are the signal data, and the blue ones are the inside ones. So it's just with a different time difference. So it confirms that we are explaining well our final variables, and this would be the reactor IBD likelihood ratio. And we will select these events. And in the other case, there are two BDTs. I'll show you here the delayed one that's fundamental. So selecting the compatibility between the two particles, and the same is the same thing. So we also see that the background, the simple backgrounds are very well described, and then the signal is quite different. So this analysis observed 9 events and that one 10. So this is in excess of 3.7 events, in excess of 2.3 events, now with a very high statistical second. So our expected sensitivity that we have after the analysis was actually, not too early, so long, that's driving this, but the observing it not much better. But then we had a upward fluctuation in both analysis, electricity, which in fact, we have a total of 14 events. So this not 19. But it's also not that these 9 are all observed there, which is natural because it's so low efficiency that we really did not optimize to the same operation point. And so. Okay, so we have 14 events, 5 common to both. We tested that this is natural. This is tested simulation. We also looked at calibration data, and this is really just from the variable we are using. And so we assume this is also true for the background, and that we expect to find this background events. And so with the combination of these 14 events compared to the treatment, we're using 3.5 sigma. So somewhat. Yeah. Well, in any case, it's interesting to understand how the selections are working and what kind of things we see. So yeah, we do look again at the time between events in both analysis and the compatible with the expectation. Then we look at the distance between them, just to figure also what it should be, and the energy of the first one. And here we are showing the data compared to the reactor using red, and then there's some little backgrounds from accidentals, from certain neutrinos, and from alpha N corrections. And this again, so this is for the delayed events, so this should be 2.2 eV. Okay, and these are shape variables that show that we are pointing, we are selecting mostly things that are pointing outside because we have more background coming inside. And this is the shape variable that's from SNO, which also is compatible. Okay, so more interesting maybe than looking at this. I want to still spend some time just explaining the main smart facilities. So the first one is the trigger model. So as we did this extraction of the signal, we to really understand the model of the trigger of the detector. So all of them. So the trigger comes from summing pulses of all the MPs in 89 seconds. And then we require this 7. And this 7 pulses correspond to 1.4 electrons which are detected. That of course, compared to a 2.2 gamma simulation, of course, it's part of it. But this we confirmed in several positions for this search, but also then already with using the different statistical methods, and we find that in fact still after working on the model and simulation is not perfect, and so this is the correction factors that we applied in relation to the simulation, and it has quite large uncertainties. Most of it comes from the fact that we didn't calibrate in all the points of the detector, so we have to use the line simulation to do that, and it's not possible. And the other one is the expectations of from the background of alpha N. So alpha N, it's in before, it's this process in which a neutron will be released, and there's something in an initial, there is something in coincidence that is a prompt event associated. And we can have this in the water. So this process, this will be this very low energy gamma ray, and in carbon. And this in the water phase only happens in the drill, but the drill is quite a high energy. And so we have to predict how much background we are getting from this that can get into the fiducial volumes in which we are measuring. This comes mostly, the alphas are expected to come mostly from polonium that is deposited in the vessel, because that will also open possible between SNO and SNO. and then it can reach into the water. So we have to, these expectations come from radio assays and measurements. Actually, Martina there is the expert on this thing. And okay, so we have this expectation that when we want to confirm with the direction. So in the around the APE, we did the same search and we get 17 events in one case, 25 in the other, with very relatively low background, but because the signal here is much higher, we use exactly the same analysis, but we added more data. That was expected less pure in other area. So these numbers were actually higher than predicted, and they compatible. The scaling factor between this and the prediction was compatible with analysis, so we scale with 5.4. And again, this then introduces higher uncertainty when we extrapolate the predictions for outside the vessel region and so to the antineutrino region. And then this is probably because there's a smaller reaching from the fluid vessel to the water than we expected in our models. But because we cannot measure it so directly in the water, we added a 400% uncertainty. That's how we end up with this large. Okay, and now I'm really finishing there. I want to more details. So this is just a question how useful can it be. So for us, it was a very nice and test of SNO analysis, the trigger model, the hot background, and of course to verify that we have a really good detector. Okay, unfortunately, it also revealed that we had a bit more of this background than expected, but I will say some more on that. It's probably not as nice, not necessarily the way to go for the world, we don't know. Super K4 has a similar efficiency in special trigger for our energy event, and their physical motivation is to search for the relative supernova neutrinos. So supernova neutrinos are easily observed as supernova was burst, but there's also diffuse background, right? What could be interesting to measure. And so they started by the dedicated trigger. What they have done more recently was to put gadolinium, this is a detector, and this releases, this should be gamma, very high energy signal, and this is much to capture time, and so they have 50% efficiency directly. They use this very low concentration, and the plan is to go this 0.1% concentration in that methods. Okay, to say that to do that, to put that inside the detector, they have to refurbish their tank. 50 kiloton tank was losing like some cubics a day of water. And so they had to avoid reaching the level. Okay, but so this is a more usual procedure, so you can just put other some isotope that actually neutrons with more efficiency. But we have to take care of the environment. So I mean, just pure water could be a good thing, we don't know. Maybe we can have many more detectors and solve this for the thing, and we can have an counting. We could have networks of that are testing, that are monitoring reactors and neutrinos or supernova, and also pre-supernova antineutrinos, so we can get signals like 2 days before the supernova explodes. That would be the network of detectors there. And we could also try to measure neutrinos in different positions, although energy is very low. So to end with that thing, I think that now we are in the we have detected full of scintillator. Before that, we had partial field. Partial field is not necessarily total. We stopped filling the detector with scintillator, so we put scintillator from the top and then extracted water from below. And when we found the pandemic came and we were not allowed to go to the detector, we were sort of at the house. and we got some nice data then. And these are already our first results of antineutrinos in scintillator to show you that now we do measure the neutron energy quite well. And of course, but we have this high background here from these alpha N interactions that now occur in the carbon node scintillators, so are a bit more hard to deal with, but we also have tools for that because now we really see the alphas, so we can count how many they are. We can discriminate alphas from positrons, looking at both shapes of the signals, and this is an illustration of that. And so we are starting to measure oscillations. This very low data set, very small data set, we still cannot really distinguish the two scenarios I've shown you, but yeah, we are confident. Yeah. Okay, and so I can end. We observed for the first time reactors in water. So it's a nice test for mostly a very, very nice test for the detector. We are now measuring the antineutrino spectrum in scintillator, so that you don't think that we won't count like 10 leads. Okay, and then they will and then yeah, so this is the big question, right? So observation of low energy neutrinos material water trend of technical achievement, and it may open the project, not this is yeah, that's the question.